Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today, we are starting a deep dive into electrical energy and power. It's topic 9 in Unit 3, current electricity. And our mission really is to explain this so simply that you never fear the formulas again. Okay, so let's unpack this with a simple observation. Something from your own home. You connect two drastically different devices, say a small mobile phone charger and a high-capacity hairdryer, to the very same wall socket.
Right, so both are getting the same standard voltage,
Right.
around 230 volts.
Exactly the same. Yet the charger is marked only 10 W, maybe, while the hairdryer, it practically screams 1500 W.
That's a huge difference in the wattage rating.
It is. So why, when the voltage pushing the electricity is identical? And more importantly, why does running that 1500 W hairdryer for just 5 minutes, why does that cost more than charging your 10 W phone all night?
That wattage difference is confusing. If the source is the same, how does the hairdryer manage to take so much more power? It feels like the amount of power consumed is the central mystery we need to solve even before we get to the electricity bill.
That's right. And let's layer a surprising paradox on top of that. Think about efficiency. Compare an old 60-watt incandescent bulb and a modern 15-watt LED bulb.
Okay.
Now, they both produce the same amount of light. They're often marketed as 60-watt equivalent in terms of brightness, but the LED consumes 4 times less electrical power to do the same job.
So if power is just the rate of energy conversion, why is the 15-watt device so much more effective?
Exactly my point. This tells us that power isn't just a number. It's a critical measure of performance, of efficiency. We need to get into the mechanics of that conversion rate. So let's start with the core idea, the zero-level definition. Power is defined as the rate at which electrical energy is converted into other forms.
Other forms? You mean like heat?
Mostly heat, yes, in things like heaters or irons. But it can also be light or mechanical work. And it is absolutely crucial to distinguish power from energy. Power is not the total amount used.
It's how fast that energy is being used up.
Precisely. A higher power rating, in watts, means a much faster conversion rate. To help us visualize this, let's use the classic water analogy. Imagine an enclosed water system, the pressure difference pushing the water.
Well, that's like your voltage.
And the flow of water would be the current.
Perfect. And any narrow section or an obstruction in the pipe, that's your resistance. So when the water is forced through that narrow pipe, its potential energy is converted into kinetic energy, which then creates turbulence and friction.
And that turbulence generates heat. Yes. Electrical power, in this analogy, is the rate of energy loss due to that turbulence. The faster the water flows or the narrower the pipe, the higher the power dissipation. And understanding this rate is essential for engineers. That's why the concept exists. They use it to calculate energy losses, to design safe systems, preventing overheating and fires, and to rate devices correctly. Now, if we build a mental image, picture the resistor itself as a tiny, highly energetic furnace. Electrical energy enters, carried by electrons, and inside, these electrons are constantly colliding with the fixed lattice ions of the material.
Billions of times per second, I imagine.
Billions. And each collision transfers energy to the lattice, making it vibrate faster. That increased vibration, that's what we feel as heat. The rate at which these collisions transfer energy per second, that is the power dissipated.
That furnace image makes sense. But wait, if power transmission lines use copper, which has very low resistance, why is power loss still such a huge concern for the electricity grid?
That is an excellent question. It cuts right to the heart of large-scale engineering, and it's why we see those giant high-voltage towers. We're going to unlock that mystery in just a moment using the formulas. For now, let's transition to the formal definitions, because exam wording is essential. Could you read out how the insert source formally defines electrical power?
Of course. It says, electric power dollars is the rate of energy transfer. It's given by the foundational expression TPI is the current, where dollars is the current and dollars is the potential difference. It also adds the total electrical energy consumed over a time period, delta T is P delta T equals VI delta T.
Great. That is our starting point. Let's quickly re-explain why PII by hours work so perfectly. Remember the definitions. V, potential difference, is energy per unit charge, joules per coulomb.
And I, current, is charge per unit time, coulombs per second.
So when you multiply V by I, you're calculating energy divided by charge times charge divided by time.
The charge unit cancels out.
It cancels out perfectly, leaving you with energy divided by time, which is the definition of power. Now, this one equation, PIE1, then leads us to 2 more critical forms. By substituting Ohm's law, that is, IR. Into that expression, we get two more crucial power formulas.
Which are P equals I2R and P equals V2RR.
Exactly. And all three of these are mathematically equivalent. They're all linked by Ohm's law.
So if they're all equal, which one should we use when we're solving a problem? I mean, why do we need all three?
That's where the practical application comes in. You choose the formula that is most convenient for the specific circuit you're looking at. For instance, you almost always use POFI OEI or torrent, or AOR is the constant quantity, like in a series circuit. And it's especially important for calculating heating effects because heat generated is always proportional to the square of the current.
Okay, so TOI is for series circuits and for heat. What about the other one?
You use P equals V2R bar when voltage, V of all, is constant, like the fixed 230-volt supply in our homes. It's the best formula for parallel circuits. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com Stanter. Let's take a quick, simple work example to see how this translates into the electricity bill. We'll use Indian standards. Suppose a powerful electric kettle is connected to our standard 230-volt supply and it draws 10 amps of current.
Okay.
Step 1, find the power. P of P equals I times V. So that's 10 amps times 230 volts, which is 2,300 watts.
For 2.3 kilowatts.
2.3 kilowatts, yes. That's the rate it uses energy. Step 2, find the total energy consumed if we run it for, say, half an hour. That's 0.5 hours. Energy, W, is power times time. So 2.3 kilowatt times 0.5 hours is 1.15 kilowatt hours.
1 kilowatt hour is 1 unit on the electricity bill.
Exactly. So step 3, if the electricity cost is, say, 10 rupees per unit, running that kettle for half an hour costs 1.15 times 10, so 11.5 rupees. Now, let's circle back to your excellent question about transmission loss. The power wasted as heat in the cables, let's call it PCA, is given by PCA equals I2RC2, where 2 loss is the cable's resistance.
Okay, the heating formula.
Yes. Now, the total power being delivered to our homes, Peter, there is $1 times V transmission. We can rearrange that to find the current, R divided by Babe pre-transmission.
I see where this is going. We substitute this into the loss formula.
You got it. The wasted power, PC2, becomes delivered 2 times $, all divided by V transmission 2. Now look at that final formula. The power wasted is inversely proportional to the square of the transmission voltage.
So V dollars is in the denominator. A bigger V means a much, much smaller loss.
A much smaller loss. This is the key. If you double the voltage, the loss drops by a factor of 4. Increase voltage 10 times, the loss drops by 100. This inverse square relationship is why engineers transmit power at extremely high voltages, sometimes 400,000 volts. It saves massive amounts of energy.
That's phenomenal. So they're not trying to change the cable's resistance. They're minimizing the current needed by maximizing the voltage.
Exactly right. Okay, now let's move on to the tricky parts. What we call the silent killers. The misconceptions that destroy marks in exams. Misconception number 1. Students often assume high resistance always means less power dissipated because it blocks current.
Which sounds logical, but I'm guessing it's wrong.
It's a dangerous generalization. The correct idea is that it depends entirely on the circuit. You must check if voltage or current is fixed. In a series circuit, the current is the same everywhere. Since pedal I2 lot hour, the high resistance component actually dissipates more power. It gets hotter. But in a parallel circuit like our homes, the voltage is the same. There, PEP equals V2R. So the high resistance component dissipates less power. Just remember, series, high R is more power. Parallel, high R is less power. Always check what's constant.
So for my home, if my 1500-watt hairdryer has more power than a 100-watt bulb, it must have a much lower resistance to draw so much power at the same voltage.
Precisely. Misconception number 2 is confusing power and energy. They are not the same thing. Power is the rate in watts. Energy is the total amount consumed in kilowatt hours.
And the bill is for energy.
Your bill only charges you for energy, the total consumption over time. It's the difference between speed and distance. Now, let's lock these concepts in with some memory anchors. First, a mnemonic. Remember the key formula PIV$ using the phrase PIV, like a disease. High power causes components to catch a disease and burn out.
That's a bit grim, but memorable.
It works. Next, a physical gesture. Hold one hand, palm up. That's your resistor lattice. Now tap it repeatedly with your other hand. Those are the electron collisions. If you tap faster, that's higher current. Or tap harder for higher voltage, your palm gets hotter. That's the power being dissipated. You're feeling the rate of energy transfer.
So I can actually feel that.
And finally, an extreme association. Think of a lightning strike. It lasts for maybe a millisecond, a tiny amount of time, but it delivers massive power, about 1 billion watts. Even though the time is tiny, that massive rate of energy transfer is why it's so destructive. So, to summarize this deep dive, here are 3 exam-safe factual points. 1. Electrical power, PLAIA, is the rate of energy conversion measured in watts. It's the speed of energy use, not the total quantity. 2. Power dissipated in a resistor is calculated using PPIA I2IR or PIVA V2R. You must use the right formula based on whether current or voltage is constant. And 3. Power transmission uses extremely high voltage to minimize line loss because the power wasted is inversely proportional to the square of the voltage. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, PROFSAM.com. Study hard, and we will see you in the next deep dive.